Hey everyone, and welcome to this explainer. Today, we're diving headfirst into the incredibly high-stakes physics of nuclear reactors. I mean, did you know that the difference between a perfectly stable power grid and a literal nuclear meltdown comes down to just a tiny fraction of a percent? It's wild. We're going to unpack the ultimate balancing act that keeps these massive powerhouses running safely day in and day out. So, if you've ever found yourself wondering exactly how engineers control a nuclear chain reaction without it fizzling out or just completely running away, you are definitely in the right place. Let's get into it.
Okay, really quickly, here is our roadmap. We're covering 1. The most important number. 2. The neutron life cycle. 3. Size and shape matter. 4. The reactivity danger zone. 5. Reactor types and safety. And lastly, 6. Real-world reactor design.
Section 1. The most important number. Demystifying K. We are starting right at the foundation.
We're going to completely skip the dense math for a second and just focus squarely on the single metric that matters above all else. It's represented by the letter K, which stands for the neutron multiplication factor. This one number tells an operator absolutely everything. Is the reactor under control? Is it running away? Or is it shutting itself down? It's just a ratio of the neutrons in one generation compared to the generation right before it. And if you want a self-sustaining power plant, the absolute holy grail is to keep this number at exactly 1.
When K equals exactly 1, we hit a state called criticality. Honestly, the best way to picture this is to think of a tightrope walker. They are perfectly balanced at K equals 1, and the entire art of running a reactor is just keeping them on that rope. Every single neutron that gets absorbed or leaks away is replaced by exactly one brand new neutron from a fission event. It's not growing, it's not dying, it's just perfectly, beautifully balanced.
Moving right along to Section 2. The neutron life cycle, surviving the core.
To really grasp how we achieve that magic K equals 1, we have to look at the incredibly treacherous journey of a single newly born neutron. Think of it like a crazy obstacle course. Now, in a theoretical infinite reactor, a neutron has to survive 4 massive hurdles. This is called the 4-factor formula. First, it's born and might cause fast fission right away. That's epsilon. Then it has to slow down without getting sucked up in resonance absorption peaks. We call that survival probability P. Next, once it's finally moving slow, it needs to be absorbed by the actual nuclear fuel, not just the water or metal around it. That's thermal utilization, or F. And finally, once it hits the fuel, it actually has to produce new neutrons. That's reproduction, or eta. You multiply all those survival odds together and boom, you get your K for an infinite core.
But real talk, reactors aren't infinite. They have actual physical walls. So we have to add 2 more hurdles to our obstacle course, giving us the 6-factor formula. Basically, we have to make sure the neutron doesn't literally leak out of the edges of the reactor while it's zipping around super fast, and we have to make sure it doesn't leak out once it's slowed down. It's pretty straightforward. A bigger reactor has less surface area compared to its massive volume, which means way fewer neutrons manage to reach the edge and escape.
Which tees up Section 3 perfectly. Size and shape matter. The physics of buckling.
This is where the physical dimensions of the reactor start interacting with the nuclear fuel. It's like 2 sides of a coin. On one side, you have geometric buckling. This is all about the physical stuff. Is the reactor a sphere, a cylinder, a big box? It measures how many neutrons are lost to leakage based purely on that shape. On the flip side, we have material buckling. This is all about the actual nuclear properties of the stuff inside, the uranium, the coolant. It's a measure of the fuel's inherent ability to sustain the reaction, its excess reactivity.
Here is the absolute kicker. A reactor hits criticality exactly when its physical shape and size perfectly match the nuclear properties of its materials. Geometric buckling has to equal material buckling. If your reactor is too small, the leakage is way too high, and the chain reaction just dies out. If it's too big, it runs away and becomes supercritical. But when they perfectly match, our tightrope walker is dead center. This elegant little equation is literally how engineers calculate the exact critical size of a reactor right from scratch.
Let's turn up the heat a bit. Section 4. The reactivity danger zone. Managing margins.
What actually happens when K wobbles away from exactly 1? Well, engineers use a concept called reactivity to track these dangerous little deviations. And to measure it, they use this totally wild unit called the dollar. I know, it sounds like Wall Street, but stick with me. When a uranium atom splits, almost all the neutrons blast out instantly. But a tiny, tiny fraction, about 0.65%, are actually delayed by a few seconds, or even minutes. And honestly, thank goodness for that, because that tiny fraction is the only reason nuclear power is even possible.
Below $1 of reactivity, the chain reaction relies entirely on those slow, delayed neutrons. That gives the mechanical control rods, actual time, tens of seconds to move and manage the power.
Think about that. Because this delayed fraction is only 0.65%, $1 of reactivity equals a K value of just 1.0065. That incredibly razor-thin window between 1.000 and 1.0065 is the entire normal operating range of a commercial uranium reactor. Like the source material puts it so chillingly, everything above that is the forbidden zone. Crossing that line is a nightmare scenario.
Because if you push reactivity to exactly $1 or higher, you hit what engineers call prompt criticality. At this point, the reactor is sustaining a growing chain reaction using only those instant, prompt neutrons. It doesn't need to wait for the delayed ones anymore. The time it takes for the power to double collapses from a nice, manageable few seconds down to literally microseconds. The power spikes uncontrollably, and it happens way too fast for any human operator or even a computer to stop it.
Which brings us to Section 5, Reactor Types and Safety, Lessons in Physics.
When you understand that terrifying prompt critical threshold, you start to see why real-world reactor design is essentially a giant tug of war. Whenever engineers load a fresh batch of fuel into a core, they don't load it at exactly K equals 1. They actually pack in up to 15% extra reactivity, called excess reactivity, because over the months it runs, that fuel gets burned up and nuclear poisons start clogging the works. They hold all that extra power back with control rods, but against that, they absolutely must guarantee a shutdown margin, meaning if things go wrong, they have to be absolutely sure the reactor drops far enough below K equals 1 to kill the reaction instantly. They even have to account for a worst-case scenario where the single most reactive control rod literally jams and won't go in.
So how did different designs handle things going wrong? Let's look at a nightmare scenario, losing coolant. In a standard light water reactor, water does double duty. It cools the core, but it also moderates, meaning it slows down the neutrons. If that water boils away, you lose your moderation, reactivity plummets, and the reactor basically shuts itself down. That's a negative void coefficient. Very safe. But then look at the RBMK reactor, which is the type they used at Chernobyl. They use graphite to slow the neutrons down and water just for cooling. So when the water boiled away, they lost their coolant, but the graphite was still sitting right there, happily moderating neutrons. Reactivity shot up. That catastrophic design flaw, a positive void coefficient, pushed the reactor into prompt criticality, which is what directly caused the Chernobyl disaster.
Okay, final stretch. Section 6. Real-world reactor design, putting it into practice.
Before a single piece of uranium is ever loaded into a commercial power plant, reactor engineers have to run a monumental sequence of calculations. It's basically a giant high-stakes puzzle. First, they use the four-factor formula and buckling equations, just to see if the physical size makes sense. Then, they boot up these insanely complex lattice physics codes to figure out how neutrons are behaving in just one tiny piece of fuel. After that, they take those results and run massive, full-core 3D diffusion simulations to predict the power flow across the entire reactor over years of operation. Finally, they cross-check everything against strict thermal limits.
And the main reason they obsess over all this math? It's all about the power peaking factor. Because even if your reactor looks completely safe on average, the power inside isn't totally uniform. You get hotspots. And the crazy thing is, the single hottest fuel pin in the entire building dictates the safety limit for the whole operation. If that power peaking factor gets too high, that one specific pin could melt. So flattening out that power distribution isn't just about efficiency. It's a critical safety requirement to make sure our tightrope walker isn't leaning way too far to one side.
So what is the ultimate takeaway here? Criticality is absolutely not just some static math problem you solve once and put in a drawer. It's a dynamic, living, breathing beast that has to be managed every single second of the day. As the fuel burns down, as the water temperature fluctuates, as control rods slide up and down, the tightrope is constantly wobbling. And it really leaves us with a fascinating question. As we start designing the next generation of futuristic reactors with molten salts and crazy new fuels, how will they master this perpetual balancing act? Thank you so much for joining me on this explainer. Keep learning and keep asking the big questions.